When a new AI model drops, the question that matters for most teams is not the leaderboard score. It is whether your stack can run it reliably, what it costs at your traffic scale, and which shortcuts will break in production. Today, we connect that headline to the engineering trade-offs behind the hype. Specifically, how a mechanism developers treat as free background work becomes the single biggest source of latency spikes derailing real-time inference systems. You likely assume memory management is just safe code happening invisibly while your model generates text or processes video. This assumption is dangerous for anyone building low-latency AI agents or chatbots where milliseconds define user experience. The reality is that garbage collection, the automatic system that reclaims unused memory, introduces non-deterministic pauses known as stop-the-world events. These are not minor glitches. They are hard stops in execution that can violate strict service-level agreements and make your application feel broken to users who expect instant responses. Consider the trade-off developers face daily. A recent study on a garbage collection approach called Bronze, published at the International Conference on Software Engineering, offers stark data. In this trial involving 428 students, those using the optional GC library completed complex aliasing tasks in roughly 4 hours compared to 12 hours for standard manual management users. That is a threefold increase in developer speed and productivity. However, that usability gain masks a critical risk where unpredictable pauses derail inference pipelines. By prioritizing development velocity over runtime predictability, engineers trade safety for convenience. But in AI systems, that unpredictability becomes a system failure waiting to happen. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The core friction point identified is not raw throughput or total execution time, it is jitter. While the code runs faster to write and less prone to memory leaks during development, the abstraction removes compile-time safety guarantees in favor of runtime reclamation that cannot be scheduled deterministically by the developer. In a factory analogy, imagine an assembly line where workers are incredibly efficient but must stop everything every few minutes for unpredictable cleaning breaks. If your product requires precise timing, those stops ruin the entire process. For real-time AI inference requiring consistent millisecond latency, these pauses cause catastrophic violations of service-level agreements that standard profiling tools often miss because they look for throughput bottlenecks rather than non-deterministic spikes. This creates a specific architectural dilemma for practitioners building production systems. If you are using languages with automatic memory management like Python or Java without aggressive tuning, your system may be introducing unacceptable jitter unless you accept significant performance penalties elsewhere. You must understand that automatic memory management is often a performance liability in deterministic systems where timing guarantees are non-negotiable. The choice becomes clear. Do you prioritize developer velocity and safety using standard GC libraries, or do you demand system determinism through manual control? This answer dictates your hardware stack. If you cannot guarantee latency, you must over-provision GPU memory and compute power to buffer against these pauses, significantly increasing operational costs. Because standard garbage collection is failing to meet the demands of modern AI workloads, new research from Stanford University proposes a paradigm shift known as neural garbage collection. Unlike traditional GC, which halts execution entirely to clean up memory, this approach uses reinforcement learning to teach models exactly which working memory entries can be evicted while reasoning continues without interruption. This method achieved a remarkable 4.6x reduction in peak KV cache size for complex tasks, eliminating the hard stops that break real-time inference pipelines. It represents a move from reactive cleanup to proactive management, where the system learns what is essential and what can be discarded on the fly based on context. The implications extend beyond just software performance into the broader economics of AI infrastructure. Research suggests that without optimized memory management like neural garbage collection or manual control, AI systems face unsustainable energy consumption and e-waste from hardware turnover required to compensate for inefficient stacks. When developers treat these systems as infallible background processes, they risk latency spikes in production environments that cannot be debugged with standard tools because the root cause is hidden inside the memory allocator's non-deterministic behavior. This mirrors a broader engineering challenge where assuming perfect automation leads to poor outcomes when real-world constraints hit. The path forward requires shifting your judgment from "does this work" to "how does it behave under load?" If you are building for production, especially in high-frequency trading or responsive AI agents, the standard assumption that memory management is free must be discarded. You need a strategy where predictability trumps convenience. The data shows that while GC makes coding faster and safer for humans, it introduces performance unpredictability that can break your system's reliability guarantees. As you evaluate your own stack, ask whether your tolerance for non-determinism justifies the speed of development or if the cost in latency and hardware over-provisioning is too high to ignore. The engineering lesson here is clear. Automatic memory reclamation is a tool designed for developer comfort, not system determinism. In the world of AI inference where every millisecond counts, relying on it without deep understanding invites failure. The future lies in smarter approaches that integrate learning into the cleanup process rather than pausing execution entirely. By recognizing these hidden costs today, you can make better architectural decisions tomorrow and build systems that are not just functional but truly resilient under pressure. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.